Hey guys, this is JSer. How's everything going? In this video, I'm going to take a look at 1488, Avoid Flood in the City. This is the problem from today's weekly contest. I didn't make it, but I was close, and it took some more time, and finally did it. So this video is about to explain how I did it. It's actually, I think it's pretty hard. It's not medium, it should be hard. Anyway, let's begin. So we are given the ranks array, which means on the first day, the first lake will be rained. The second day, the second will be rained. The third lake will be rained. Yeah, something like this. So on each day, I can do two things. One, if it is rains, I can do nothing, so -1. And if there is no rain, I can choose a lake to dry it. So for the case here, our goal is to avoid flood. For the lake will be first empty and then full once it rained. And if it get rained a lot of time, it's gonna flood. Okay, so for 1, 2, 3, 4, definitely there will be no flood risk. So we do nothing because there will be raining all day. So we do nothing. And here, so the first lake will be full, the second will be full, and we have 2 days to dry. Of course, we can dry 2 of them, and then these 2 lakes will be rained again. But there's no flood risk, so we return this. Do nothing, dry 2, dry 1. And 1, 2, 0, 1, 2. We have only one day to dry. Either we dry 1 or dry 2. It's gonna be full here, right? So it's impossible to avoid the flood. We return empty. For a case like this, we have 3 days to dry. We can dry it on any day, so it's okay. Something like this. Either numbers will be okay. Yeah, it's acceptable. And the lake is infinite, so here, yeah. One thing to remember is that even we cannot dry any lake, even it is already empty, we still need to dry something. Yeah, dry empty lake, still it's valid, but it would not change anything. So 10, 20, 20, no days to dry, and empty. Well, let's analyze the general example should be here, this one. Okay, so the lake has 3 states. First is empty, then full, then flood, right? So actually we can pick up the the lakes which is full. So after the day 1, the full lake will be 1, right? And after day 2, it will be these 2 lakes are full. So now we have several days of non-raining. So we must dry some lakes. But which one should we choose? Well, if we choose one here, the next rainy day will be 2, so it will flood, right? So we need to choose 2. So remove 2, and then these 2 come, it will not flood. And the next one is 1. So on third day, we dry 2. We left 1 is full, and on 4th day, we remove it. So it's all an empty. Now we can safely add to 1. So you see, when we have 1, 2 full, we actually need to choose, like say, actually, if there's 3 here, suppose, we still need to choose 2, right? If you don't dry 2, it's gonna be rain. So yeah, it will flood. So we need to choose the closest full lake, which are to be rained. So now for day here, we have these full lakes. So we need to search the from the 4th day to find the lake that's gonna be rained. the closest one. So the closest one is 2, right? Cool. So yeah, let's do it. The idea is become clear. The use a set to track the full legs. Search for the first full leg to be rained on non-rainy day. Yeah. So the full legs would be new set and 4. If it's 0, to do search. Okay, I just used to do. If it is not, we will do nothing, right? So I'll say let it be. Let it be. Range I. I'll create a function called function let it be. This should be a lake. So let it be. It should be. Oh, we need to return the actions, right? Actions. Let it be. Okay. If there is already a full, so it's gonna be error, right? So if a full lake has lake, if has it, we return the okay. Yeah, we return false, the error. If not, we set the full legs at lake, and the actions should push -1. This is do nothing, right? So return true. Cool. So this is let it be. So when you let it be, like this is safe. If not safe, we return empty. This is it. Let it be. Let it be. Cool. Now, if it is 0, like the case here, we need to search for the loop through all the rest element to find if any of them is in the full legs, right? So there should be a next lake soon to flood. So let j equals I+1. We search for the next one. Yeah. And while j is smaller than something, j+1. If it's already full, so the if range j is not 0 and the full legs has it, we break, right? We break, and it will set the lake soon to be flood. It's range j. Cool. Now there might be no such lake, right? So if we found it, we need to what? We need to dry it, right? It's just dry. Dry. Lakes to flood. We create a separate function. Oh, there should be not like this. Function dry lake. When we dry it, it should be full lake. Delete lake actions. We need to push it. Cool. So we dry it, and if it is not there, what do we do? Well, we could dry any lake, right? So we dry any lake. For any lake, if something is in our full lake set, we try it. If not, we just set a number 1, right? Any lake is okay set. Try any lake, be if full lake size is full lakes, because it's set. So we try it, and if not, we just try 1. Right? Cool. So this is it, I think. And finally, we return the actions. We run. Oh, unexpected token. Oh, here. Yeah. For example, here it works great. Let's submit. Oh, I tried a lot of submissions and finally got it through. It's sure to be a time limit exceeded. Let's see what happens. Before we improve it, let's try to analyze our current solution here. There's a for loop here, and for each item for 0, we search for the rest, right? So ending with a set is okay. So generally this should be quadratic, right? And with a space of linear space with a set. So this is not good actually. Let's try to improve it. Before we improve it, let's analyze what caused the time limit. We're getting the input like this, and a very long series of days raining, and this is like flood season, rain season, and this is dry season. So this is a bunch of zeros. We need to, okay, our solution here actually, for each 0 here, I'll search for all the rest, right? All the rest, and then here all the rest, and then all the rest. For extreme case, like 1, 0, 0, 0, 0, 0, 0, 2. For this one, I search the whole and find there's no one. Okay, I'll go 1, 2, 3, 4, 5. For 1, I'll search the whole elements, find there's nothing, and then again I'll search the whole, right? Find nothing. So when we go to these 0, we realize that there's already 4 zeros, right? There's 4 zeros. We are sure we can't just try them all, right? We're sure. So we don't need to traverse through all the elements, right? Yeah, with this, yes, when we found 4, 0, it means there is no element before this 0 that is full. So when we made this 0, we could stop. There's no more need to check. We can safely just try all of them. But if there's a 3, 0, we should still searching. We don't know whether next one is 4 or 3 or 2 or 1, right? So actually we could improve our solution that could count the 0 and stop. Improve the search here. Yeah, let's do it. So here, if we found something like soon to be flood, cool, and we need to actually count the 0. Let the kind of 0 count. Okay, it should not 0 count, but no rain day count 0. If that's the case, we should start from I, right? Okay, let's start from I. Doesn't change. And if range j equals 0, then we plus it. Increment the non-rainy day count. And yeah, and if this rainy day count equals to the full lake size, we break. So now J stop at enough zeros, or the first for or the soon lake to be rain. Well, if we found the lake, then we draw it, and if not, we try any lake. So this should work. Also, let's try. Looks like still TLE. Well, we're accepted. It's very slow. Let's try to improve it more. Our improvement here actually stops for 0, but like for stop 0 here. But when we go to the next one, here 0 here, we stop that here, and then we will try 1, right? And then we go to next 0, we still will search. Suppose there is like k zeros, and before we're going to actually basically for the length, okay, range of count is n, continuous 0 is k. Before we actually will, for this bunch of zeros, it's gonna be kn, right? OKN. Now after, it is the full lake size. The size here, so it improves a lot. Oh, times k. But still, maybe we can improve it. We don't need to times k actually. When we found these enough zeros, we could just try them all, right? Just try them all. We don't need to search again. So actually here, we could improve something. It's like a lake soon to be flooded. We found it, we try it. We found it, we try it, and then we could just try for the leading non-rainy days. It means, suppose we need to find 4 zeros, we find 3, like something like this. We will stop at this 0, right? We stop 0, but we could just try for the leading zeros already. There's nothing. Okay, this is 5. Suppose there will be no 1, 2, 3, 4 before this 0. So we try them 1, 2, 3. Either is okay. And we cannot try to 0, 0, but because there might be 4, 5, 5 here, right? Yeah, cool. So here we try any lake. We just for it k equals I. K will stop at j. K plus plus. So if means k is not 0, is 0, we try any lake. Oh. If not, we break, right? And when we're driving the lake, we need to update I to avoid the unnecessary searching. So after we try, we set I to k. And I will be incremented in this for loop, and I will be k plus 1 for next iteration. So now we improve it. So actually for this 0, we didn't search it again. We go to this 0, and we just flood them. All right, we search once, and then we flood. We dry them, and then search it again. So what's the time complexity now? So each node, each element here, like okay, for non-zero, of course we add it and done. For 0, it was search, go to the stop at certain point, right? Certain point, 0, and then we will dry the full legs, right? So we will loop through this K again, this bunch of nodes again, and 1, 2, 3, and then go to here and here, search again. What's the time complexity? Well, research. Could we just these will traverse once, and these will be traversed like so the worst case actually here should be like 1, 0, 1, 2, 3, 4, 0, 5, okay, 6, 0, 7, 0, 8, 0, 9, something like this, right? I'm not sure. So this should be the worst case. So this was the maximum 0. It means like the 4, the maximum here. We search to here, and then we will dry it, and this one will be assigned. This will be drawn. Ah, yeah, I see. So even for the worst case, every node is actually traversed for like we search for 1, 2, 3, 4. We search here and go here, got 0, and then we need to search it again. And then search again. Well, I should say for the worst case, for each node actually, it's still worst case is still the same. But averagely, let's averagely, if it's not something like this, it's about just some bunch of non-zeros and zeros, non-zero. If averagely, I think it's close, similar to linear time. I don't know. Because we search for the J, it depends on how far we can go for this K. Averagely, if it's only 1, then it's gonna be K again, right? So it's n squared, but if it could be far to K, then it's close to n, linear time. So that's my analysis. Let's try to submit. Cool. We're much faster than the previous one. Improved a lot. Yeah, that's it. The key is depending on how far we can go from how far we can get K closer to J. Yeah, that's it. Hope it helps. I'll see you next time. Bye bye.